showing on Zoom though.
So, so you can't really see me on the screen, but I wanted to introduce our speaker. We're very lucky that we got Walter Dempsey to come since my email thinks that his email is trying to destroy me, so we can't really contact each other very well. So Walter is an associate professor of biostatistics at the University of Michigan, and he has worked with some pretty outstanding people. He did his degree at the University of Chicago. Was it with Peter McCullough? Who is somebody that's been famous since I was young, so. Uh-huh. And he did his postdoc with none other than Susan Murphy, my evil name twin. People think that I'm her, and it's not fair to her. Walter is joined here by one of his, let's say his best student, his favorite student ever.
Sure.
Favorite student ever.
As well as 19 participants online. And he's going to be speaking about learning while training in inference after optimization. Thank you very much, Walter.
Thanks for the invitation. And oh yeah, I'm happy to give this talk. So my two things on this. One is I just talked to a bunch of applied people. So I'm trying to transition how I'm talking now to more a statistical audience. So bear with me as I kind of reorient myself, because I just literally finished talking and then drove down here. The talk I'm going to give, I saw Suraj's slides, but I don't know how much he talked about mobile health broadly. So I'm going to give sort of an overview of what is mobile health, what the area is in terms of deploying these learning algorithms, the challenges in terms of deploying online statistical learning algorithms in the real world. And then I'll move and change to a slightly different topic if I have time on statistical inference. Specifically, I'll talk a little bit about selective inference. So the idea here is that in a lot of these studies that we run some learning algorithm, we collect some data, and then we have questions about potential other variables that might be important for effect modification. The natural way to do this is then what a lot of applied people do is they'll go one at a time and look at different potential modifiers, and then based on statistical significance, they'll say, okay, one at a time analysis, these are the top 20, and go from there. What we're going to propose is more of a joint exploration analysis that uses sort of a penalized method, and talk a little bit about what that method is. But when you use penalized methods, it's hard to do inference after that. So selective inference are tools to actually account for selection. And so I'll talk a little bit about that as well. If I can go to my next slide. There we go. So today I'm going to give you a very brief overview of MRTs. I think I have like 45-ish out of 50, the standard amount?
Yeah.
Okay, I just wanted to make sure before I start talking, and you're like, it was only 30. So I'll talk a little bit about MRTs and JEDIs, or just-in-time adaptive interventions, give you a sense of what those are. Then I'll talk about how to build these policies, and then I'll talk about selective inference. For some reason, it's not letting me go to my next slide. I think it's somehow zoomed in. I don't know why it's doing that. Interesting. All right, I'm gonna do is I'm too annoyed. I don't like how it's showing, so I want to make it a little bit easier for everyone to see. It getting cut off is going to annoy me the entire time I'm talking, and so it's better to just try this. Oh, it yelled at me. It shot me out. Okay. Well, let's go Chrome. Let's see if I can do one more. I'll try one more try, and then I'll actually talk. Mine. There we go. Yay. Yeah, there we go. Okay. I also use all Michigan theme slides, so that's nice. There you go. So what is an MRT? So micro-randomized trials actually were introduced by Susan Murphy, my postdoc mentor, when she was here at Michigan in the statistics department. The idea behind them is primarily motivated from questions in mobile health. What is mobile health? Mobile health is just the use of mobile devices and wearable sensors to monitor individuals outside the clinic and use that information to provide interventions. So these interventions typically take the form of mobile interventions, though you can think of like messages through the app, information you can get through apps. So how you present the information in an app is also a mobile intervention. They also include things like text messages. There's biosensor feedback ones as well. This example is just to kind of explain why we have MRTs. So MRTs are an experimental design to answer questions about what are called just-in-time adaptive interventions. So I call these Jedis because it's much easier. And Jedis, again, Susan was a big Star Wars fan, so I think she's actually more into Star Trek, but she liked the name, so we call them Jedis. The idea behind a Jedi is that in chronic illness populations, you have individuals who are in need, but you want to provide the right type of support at the right time for those who need it, and so you need just-in-time support. So this is this idea that when you have an individual in need, you need to provide a support in the moment in their natural environment. And so in the context of physical activity, or in the context of like a hypertensive population or a sedentary population, you might think of these interventions that are providing suggestions for promoting physical activity. So here what we have is a 6-week physical activity run by a professor in the School of Information at the University of Michigan. This 6-week physical activity trial was providing interventions over time and using a Fitbit tracker and a mobile phone application. The study was called Heart Steps, and the question it was trying to address is, can we derive or devise a just-in-time adaptive intervention to improve physical activity and through this improve long-term health outcomes? The app is on the right, so it just, if you want to think about it, right, it's just your standard, everyone has applications on their phone that ping them. It's the standard thing of like you get a ping on your phone, you look down, and here's an example of a message you could get. I'm just going to read it out loud, it's a fun one. So what warm, healthy treat could you make today? Maybe tea or soup. You could do squats or jumping jacks while the water heats up. So this is like, again, I would not say, do not ask me many, you can ask me questions about how these messages are generated. They are not my expertise. There's a whole area of behavioral science that goes into how to build these message pools, and now people are using LLMs and things like that to build these in a more scalable fashion. In terms of the design itself, I like showing the sort of schematic to understand what's going on. So again, we're trying to understand when to provide these interventions. So when we have questions in the context of an experiment, or we have questions about sequential treatment, we often think of sequential randomization as a tool for answering statistical questions like this. And an MRT is just a sequence, a sequence of micro randomized moments at which we could potentially receive or send a tailored message. So in Heart Steps, in all of these MRTs, you have sequences of observations, actions, and rewards. The idea here is the observations are a mix of wearable data, mobile data, self-reported data, sort of everything you collect on an individual between time points. After you collect these observations, before you provide an intervention, you assess a few things if they're eligible for treatment. In the context of a mobile study, you're eligible if you're not driving a car, if you're not walking. So if these are sort of questions about feasibility or questions about ethics around sending a message. So in a physical activity study, if you're driving, I shouldn't tell you to go for a walk. That makes no sense. If you're currently walking, you should also not send you a message to say go for a walk. So these are the two things that we measure before. And so these are sort of eligibility criteria, these two right here. Once we know you're eligible for randomization, we then randomize you to potentially receive a message. So this R here stands for randomization. This coin flip, it's not your standard 50-50 coin flip. Here, it's typically depending on the number of decision points in the day and the dose constraints you'd expect to want to satisfy. So here, an average number of treatments of 3 was deemed tolerable. So the coin flip was like 3/5 probability of receiving a message. That's all I had.
Are the messages either send one message or not, or are there multiple options?
Yeah, so in more recent versions, there is sort of send message versus not, and then if you decide to send a message, what type of message? There's sort of multiple factors you can vary across them. For today, it's the basic action of just binary send message versus not. Also, because everyone's on Zoom and I can't see them, if people have questions, they should feel free to interrupt me. I can't even see the Zoom chat, so I'm just going to keep talking unless I see hands.
Yeah, we've got 26 people on Zoom.
Oh, great.
So Somebody says the presenter needs to share the screen. Is that per?
I can do it again.
You cannot read the
I don't know if it
projection
actually
on the
got
screen.
shared. Did it not get shared before? We can do it now. Can
The
you
projection on the screen.
see this now?
Yeah,
Yeah.
Thank you.
Awesome. Well, most of what I said so far is not, you didn't need the visual for. So this is the first visual that's pretty important. So I'm glad I can share this one. Again, just for those of you online who are just finally seeing the slide, again, you have observations on the far left. You have actions or decisions you're making in the middle, and then you have proximal outcomes here. So we think of these as observations, actions, and rewards. And this sequence repeats itself multiple times in an MRT. So you don't just do this once. In Heart Steps, it was 5 times a day for the course of 42 days. I should mention one other thing. The question just that was raised earlier was about what type of actions do you take? Even though I'm going to focus on binary decisions, sending a message is still tailored to your individual context. So the action of sending a message does not mean it's sent a general message. The message being sent is tailored to weather, location, things like this. So for example, if it's currently raining outside, we're not going to ask you to go for a walk outside. If it's the weekend and we know you're with your kids or something, you're not going to send a message about going for a run. There's just natural things that we'll take into account when deciding what types of messages to send. The action, though, I'm going to focus on is the binary action of sending the message or not. So I talk about this as tailored messages, and we're going to talk a lot about today about personalized decision rules, which is this R. So there's tailoring and there's personalization, and I'm just disentangling those two. Hide myself up here. Okay, so this is a group of statisticians. I don't really, maybe I don't need to say it as often for this group, but I like saying it because, again, some people ask this question. So why micro-randomize? Well, it's because we have questions about causal effects. And so randomization ensures we can assess them. And so by randomizing, we can assess questions or answer questions like, should the smartphone send you activity suggestions to increase your proximal physical activity? Does this effect vary with time or current context? And the sequential randomization allows us to answer questions about sequences of treatments. So we're not just interested in asking a question about one time point. We're interested in understanding sort of the time-varying effect of these messages. How did the policy that we're building out, how does that affect sort of distal outcomes? So we want to understand how the treatment has to be adapted across time and changing context. Okay. So the first part of the talk is over. The second part is on this sort of extension that we've been working on. Specifically, the R in my Heart Steps was a simple coin flip, a 3/5 probability coin flip. And in a lot of more recent studies, the question's being asked, okay, we should be thinking more carefully about, for Walter, if I'm in the study, maybe that decision rule should reflect the data I've collected on Walter so far. So if I have a lot of information on an individual, I want to personalize the decision rule to that individual. So what we've been working on, these are the area of reinforcement learning comes up here. And so Susan Murphy, the reason she was very interested in MRTs was to collect data to build personalized decision rules and think about online learning. So here I'm going to talk a lot about when you're in the course of collecting data, you're going to change that randomization probability to reflect if you think it's a context in which the individual would benefit from treatment, that randomization probability will increase, meaning you'll get closer to 1. If it's a context in which the intervention is less effective in improving the outcomes, you might have the randomization probability decrease. And so I'll talk a lot about, I'm going to try and balance two things. I have some statistical points that are more technical, and then I have a few more practical points about the decisions we made for deployment. So the study we deployed this in, the study I'll focus on, so we've done this in 3 studies now. I'm going to focus on low salt for life because it's probably the simplest one. It's also the one that I can actually point you to a paper that we've written that actually exists. So that's the other reason I talk about it. This is a study of people who are hypertensive. So it's a hypertensive population. Also, for those online, I wander a lot. So I always worry that they can't hear me. So let me know if I wander too much. I can stand still more. So it's a hypertensive population. They get an app called the Low Salt for Life app. What is that app trying to do? Well, it's trying to promote the use of low salt alternatives for individuals with hypertension. How do you promote low salt alternatives? Well, there's a bunch of information in the app about if you're interested in buying bread, what kind of breads are low salt, low sodium alternatives to the ones you might consider. And so what we end up doing in this study is that we measure through wearable devices where you are, and we have sort of these proximity-based GPS rules that were built by a software engineering team to say the individuals arriving at a grocery store or restaurant. And so this is something I did not build myself. This already exists. There are some problems with it. If you're interested, we can talk about it. But for now, I just want to think about it as once you arrive at a grocery store or restaurant, we're going to randomize you to potentially send you a notification. That notification is trying to get you to get into the app to look at low salt alternatives to when you're in that location. The approach we take here, so there's a couple different versions that we've built over time. The one I'm going to talk about today is called a Thompson sampler. It's a contextual bandit algorithm. A contextual bandit, I don't know whether I don't know the sort of the etiology or whatever of bandit, but for contextual, it's just the fact that you're using the context to decide what to do. Thompson samplers actually, I think, were invented in Michigan in the stat department in like the 60s. So it's been around for a while. It's really a Bayesian algorithm. So it uses a Bayesian posterior to decide when or with what probability to send a message, right, or to take an action. So what do you need to build a Thompson sampler? Well, you're going to collect a sequence of context, actions, and rewards. You're going to fit a model to the data you have so far, and it's going to be a Bayesian model, so you're going to have a posterior, and you're going to use that posterior to decide what actions to take the next turn. Here, my action is binary. My context, I'll talk about in detail in a second, but you can think about this as just your current context that you're in when you're arriving in a grocery store or restaurant. And my reward here is just a binary reward of whether you open the app in the next 30 minutes. So you have a binary outcome, a very natural thing to do for statistical models is to choose a logistic regression model. The first question you have to ask, though, this is not an offline setting where you get to try a bunch of different models and see which one fits better. You have to think pretty carefully about model complexity. So here you're fitting a logistic regression with data you're collecting online. So early on, you have very little data. The first time someone arrives at a grocery store, you have no data. Later on, you're going to have lots of data. So the first question is, what model do you want to fit? And you can either choose a really simple model. So the top one is a simple model in which you have actions mattering, but they don't interact with context at all. So this model would be one in which maybe you just send with some probability, depending on a really simple, okay, the action just improves my probability with some fixed amount. And then I have a really complicated model. So what do I mean with this complicated model? Well, all of my covariates that I'm collecting, I have about, I think, I wrote P of them. I could include all first order interactions with the treatment. I could include all second order interactions with the treatment. I could include all, third order, etc. These models get ever more complicated, and there's a trade-off. You want to build a complicated model because you want a model that reflects reality. So you want a model that fits the data well and will learn in what context it's appropriate to send messages. But the more complicated a model, you have two problems that will arise. One is, with limited data, you might actually end up with separation in a logistic regression, which is going to break it. So there's some problems of just fitting the model is going to become a problem. And the second problem is you're going to need lots of data to even learn anything. So the more complicated model you need to fit, the slower it is to learn in what contexts matter and what don't. And so this is like the trade-off that we have to think about in this field. The second trade-off is that even if you've picked a model, so right now I'm just going to say, okay, I picked a model, you then need to think about what priors you're going to use. And so here, it's funny, I actually showed this slide in my applied talk and I said ignore all the math, but I had to show the math because it's like, you're a statistician giving a talk to applied audience, you have to show one slide with some equation. So here, what I want to highlight is there's a really nice paper by Andrew Gelman on the use of weakly informative default priors. The idea here is if you're in logistic regression with binary outcomes and you're really worried about complete separation, what can happen is, or what you want to exploit is the fact that you want to use a shrinkage prior, but you really want to shrink higher order interactions more than the main effects. So the idea here is he'll use centering tricks in his code. Unfortunately, I couldn't use exactly the way he was doing it because I was using PyMC3 and Python didn't let me do it. But the basic idea here is if you look at my priors, my main effects, I'm assuming a Cauchy prior with a beta of 10, beta of 2.5. But the three-way interactions, I'm allowing them to exist in this model, but I'm shrinking them to almost zero no matter what. So what this allows us to do is when we have very limited data, we can fit these models. However, when the data grows, if there's a lot of information saying this three-way interaction is important, it allows it to turn it on over time. So it sort of balances these two things. And the way we do that is we say higher order interactions, you need to penalize more than main effects or two-way interactions. The second point I want to make is, if you think, okay, if you go to a grocery, I would say, this is me as an example. I go to the grocery store probably 4 times a week. That might be high. It's because I have 2 small kids and you forget things all the time. But on average, people go to grocery stores maybe once or twice a week. You're looking at maybe 3 months of data. That's not a lot of data on a single individual. How are you going to learn on that person? And the way we handle this is we actually use hierarchical models. So we basically partially pool information across individuals. So everyone in this population has hypertension. We're thinking it's a somewhat homogeneous population. And what that allows us to do is, if you look at the black box here, we're basically saying, you know what, we're going to partially pool information in which you have random effects for individuals. Those random effects are allowed to turn on, but we're penalizing them a lot as well. So I'll pick on Suraj because I know him. Suraj and I would have our own person-specific effects dependent on context. But early in the study, if Suraj enters the study late, there's about 100 people in the study already. I have good estimates of the fixed effects, and I use those for Suraj early on. But later on, if he's very different than the average individual, I'll learn that from the data I'm collecting.
And all the time on the left-hand side, we're modeling whether somebody opens the app or not.
Exactly.
Not if they take an action. It's just if they open it.
Exactly. So there is some nuance here. We get into the paper. There is the what you want them to do and what you're able to measure problem. So basically you have a behavior you're hoping that they have, which is I want them to choose low salt alternatives. You can't measure that in real time. You can ask them, did you choose low salt alternatives? But they'll probably just say yes if they respond. A lot of people So I don't know how trustworthy it is. So people will say, okay, well, you should just use gold standard measures, but the gold standard measure in this field is like a 24-hour urine sample. So it's like this really intense process. You can't do it that often. And so we chose this engagement measure because early on, no one knows what the low salt alternatives are. So they kind of have to use the app if they're going to engage in the behaviors. Later on, it's probably not a perfect proxy because if you get used to it, after 2-3 weeks, if I'm just I now know, okay, instead of choosing this peanut butter, I choose this one. You get that behavior is built. It might not be a perfect proxy, but at least it's a proxy we feel okay with for the early stages of the experiment. And later on, it'll sort of oversend a little bit more than you intend.
And then very briefly at the end, as they become well trained, they're going to hear the little notice, and then they're going to know that they're supposed to choose and never open the app.
Exactly.
Because they're so well trained.
Exactly. So in that case, what we learned later in the sort of later stages, which one of our covariates is the stage of the intervention. So in the later stages, we're hoping that happens. Now, whether that happens or not is a different question. If it happened, our algorithm should learn to not send the intervention as much, because then you're just not opening the app. But again, the reason we penalize you towards these baseline models, which means you're really not going to learn that too quickly. So it's still going to send it pretty often. We also we put boundaries, so you can never go to 0 or 1. There's always a minimum or maximum probability of being sent. And so these I'll explain how you go from these pooled models, these shrinkage priors, into an actual probability of sending. One other problem I just want to mention is in these sort of online settings, you don't have everyone arrive into your study at once. People get accrued over time. And so you have to think a little bit more carefully than traditional analyses, sort of offline analyses, because now what does it mean? What data are you using when you decide to fit this model? And so we have sort of this partial pooling happening, but people gradually enter. And so when it's your turn to update your model, so we updated the models at sort of every 2 months, we use all the data available. So even if someone hasn't reached their 2-month marker, they're getting included in the update for this first person. And so this allows us sort of partial pooling rules with gradual recruitment. Madeline Abbott, who's a student here who graduated, she came up with a nice rule going back to my model complexity point. of when to incorporate higher order interactions. Well, we have this nice rule that you sort of, how often do you see different combinations? And as long as, once we had enough data to potentially estimate that effect, we included that interaction term up to, I believe, three-way interactions. So we never went beyond three-way interactions, but we said, okay, you can only turn on three-way interactions once we see enough combinations. Another problem that's going to come up with this is, again, like, actually, let me skip. I'm not going to talk too much about that yet. I have a nice slide on that. Okay, so what is this algorithm doing? We're balancing model complexity by having this rule that Madeline and I worked on, that's sort of deterministic, with shrinkage priors. What we're trying to get is the best of both worlds. And what this slide is trying to highlight for you is that balancing act. So there's the two extremes I talked about. There's the complicated extreme where you just fit a gigantic model with all the different terms in it. There's the simple algorithm, doesn't include any contextual moderators, and there's low salt for life. On the left-hand side is this plot, which is example A. This is when the truth is a really simple model. Imagine you were generating synthetic data or simulating data, and the truth is that there's just really no moderators of treatment. In that case, simple should be the best. So regret is how bad did you do best compared to the best policy. So the green line being the lowest just means simple's outperforming everything else, which is what we want on the left-hand side. But you can see low salt for life doesn't do much worse. The complicated model does a little bit worse than us, and that's because, again, when you have many parameters you're fitting, you're paying a penalty because you're fitting these gigantic models. When you live in the actual true world of having many potential contextual moderators, you can see the simple model starts failing. You have lots of regret. Your algorithm is not performing well, so green line being the highest is not doing well. But our algorithm ends up doing almost as well as the complicated algorithm. So you can see that we're sort of matching up with the sort of complicated performance you get from just fitting this gigantic model. The other thing is someone has to pay for running all these models. So we're fitting Bayesian models using MCMC many times on hundreds of individuals. The bills started to rack up. And so if you fit the complicated model, you pay lots more money. And so the low salt for life algorithm is sort of, it actually runs in finite time. It actually doesn't cost thousands of dollars. So it was sort of a nice alternative for us to consider. Okay, so now how do I convert my output into a randomization probability? It's actually a pretty simple calculation. And so what we do is, for a given context, X, we look at the probability of sending of opening the app given that context and the action is equal to 1, meaning send the message, and compare it to that probability for the model when of opening the app in that context and not sending the message for a particular value of beta. And that beta has a posterior, so we just integrate over the uncertainty in that beta. So remember, we just have a logistic regression. Beta is sort of the underlying parameter. We're just asking how often for a particular beta is it better to send than not send. And then we're averaging over the uncertainty, and that gives us that probability. Yep.
This is assuming that somebody's opening the app without a message being sent.
Yes.
You have to.
Yeah. So I was going to talk about it, but since you brought it up, no, it's very helpful. So this basically says, okay, you have to open the app. Even if I didn't send you the message, we're basically assuming that you're going to open the app. We do have in a lot of these algorithms a cost function as well. So what we'll do is we'll say we don't just compute the probability of these two, but we actually compute this probability and we compute like a cost of sending a message, and we'll subtract that cost. So it's not that it's just greater than this, but it's greater than this by some amount. And we'll use that kind of function as well. But yes, these types of binary actions become quite difficult because so it does turn out that people do open the app even if you don't send them, but it's still infrequent enough that you end up with it being the cost can help you offset that issue. What context did we use? So I'm just showing you. So when you deploy these, you need to basically a software engineer to also deploy this. So this is in real time. Every time you get to a grocery store or restaurant, it sends it to the cloud saying, hey, I'm here. Here's my context. We have an algorithm sitting in the cloud saying, send with this probability. In more recent studies, when we have like 4 software engineers, we can do that in real time quite easily. Here, there was 1, and so it was quite hard to do. So what did we do? We basically built a mega table, called it. A mega table is just every context is categorical. I think there's 10,000 combinations of context. And so what we did is we basically said there's a Walter February mega table. So all my software engineer needs to do is look up my mega table on sitting in the cloud, look up the correct row in that mega table. It says with probability 0.7, send the message, and then we randomize according to that. So they don't have to do any on-the-fly computation. There's just a mega table sitting on the cloud that they get to call, and this is how it looks. For those of you who've worked in clinical trials, you know that there's a lot of study monitoring that goes on with clinical trials for adverse events, various things. Oh, thank you. Here, we now have an algorithm we're also deploying. So not only do we have to deploy the algorithm, we actually have to write code to monitor the algorithm. So now not only are we interested in trying to design this Thompson sampler, we also have to make sure it was implemented correctly and document any gross deviations from what we expect in terms of behavior. So how do we do this? Basically what we do here, and this is actually not Madeline, this is Rachel Gonzalez, who's another student I work with. What we look at are sort of the calibration of our algorithm. So in every given context, we have a probability of sending a message. We know what that probability is at every time. We also know how often these messages were sent empirically. We can just say, okay, if you're in this bucket where I said between 0.65 and 0.70, well, I should see roughly 67% of the time I'm sending a message. And so we check this using this kind of plot. And so this is just showing the distribution, the sort of interquartile range for all of these different probability bins. The reason we did this is you want, I'm going to say it in a nicer way. Software engineers are not statisticians. They don't really think, once something's implemented, they assume it's just, it's randomizing and therefore it must be doing the right thing. And there's been a few times we've been burned by that statement where we end the study, even in the simple coin flip example I gave you, you'll think, oh, yeah, it's probably, how could you screw up a 3/5 probability coin? Well, there are many ways you can screw up a three. I'm happy to explain a few of them. And so as we move towards these RL algorithms, we've had to build more monitoring software to actually say, okay, and this isn't a simple, yes, no, this is a statistical check that we have to do it every single time. So we have basically statistical checks of gross violations from calibration that we're checking pretty much at the weekly level. Okay. Yeah, I'm going to skip. So I have a nice fun math one, but I'm going to skip this today for time. Basically, we built a newer version of this. I'm just going to highlight the main things, which is this Bayesian algorithm takes forever to run. Why does it take forever to run? Because you're fitting a massive MCMC every time you want to fit this model. MCMC is very computationally expensive. You have to then check that the MCMC, the chains are converging. It was fun the first time. After that, it was like, this is a nightmare. I think it was Madeline at first and Rachel had to weekly be checking all the chains to make sure they were converging, that we had no weird behavior happening. So what did we do? We said, oh, what are you really doing when you're being Bayesian? Well, you're really just using the posterior as a way to perturb a point estimate, to get some notion of sort of capture the uncertainty in this point estimate to explore in different directions. And so in more recent studies, this algorithm, which we call ROME, robust mixed effects, something. ROME was our attempt to move away from a pure Bayesian algorithm. So what did we do? We've said, you know what, when you're solving these problems, really you're just interested in getting a point estimate using simple, least squares or simple penalized least squares. And then all you need to do is actually inject some noise into that point estimate based on the variation in the data. So you use some variance estimate. And so what ROME does is it basically avoids all the MCMC problems that plagued my life for 6 months. And so we're moving more towards, and I just wanted to highlight this here, and if you're interested, I'm happy to talk about it more, algorithms that are scalable. So instead of having it be, I can only run this thing every 2 months because I have to fit this large Bayesian model, I actually also have to check convergence, etc. Now we're moving towards algorithms that can be fit pretty quickly. There's still some computational issues. And only you need to think about perturbation of point estimates rather than full posterior distributions. The paper was in NeurIPS, I think, a couple years. Oh no, it wasn't this year, it was last year. And we just showed that we outperform a few different methods. I'll say one more thing here, and then I'll move to my other topic, which I wanted to briefly cover. We're now deploying this in the intern health and the Compass studies, so there's more interesting recent ones where the question that was asked earlier, we're really trying to think about multiple actions, so not just binary send message versus not, but how do you think about multiple actions? How do you pool information with multiple actions, or do you how do you treat them all separately? And also, how do you incorporate delayed effects? So one of the things that Thompson samplers do is they're myopic. They basically just care about your current actions and whether or not you're going to improve your current proximal outcome. But really, we're interested in long-term health outcomes. And so we want to think more about delayed effects of these messages and thinking about redefining the reward to account for those delayed effects.
Is corral like sort of horses, putting them in?
Yeah, so corral is the horses. So basically, we have multiple people proposing multiple bandit algorithms now. And the corral is actually trying to corral the multiple algorithms. So that's the idea behind it. Here, I'll mention two things on it. The first one is when I talk about model selection, right now we have this rule that we built to build out our model. In other settings, it's hard to do that. And so those settings, what we have is the corral is you have multiple instantiations of your bandit algorithm. So you have one that uses very little amounts of data in terms of the model being very simple, and then you have one model that's really complicated. And instead of choosing one a priori, you let them both run, and the corral figures out which one is trying to do a better job of fitting the data. So the corral component is this idea that you do pay penalties for this, so you shouldn't, it's sort of like horses, right? If you're trying to corral 2 horses, it's much easier than corralling 20.
Yes.
And so here the penalty is exactly the same as the model complexity issue around if you're trying to corral 20 models, pick your best one, it takes some time and you take some time to learn them, but because they're sort of all nested families of models, it actually isn't that bad. Thanks. Yeah, no, of course. Other questions? I'd like to stop here before I move to my next section. So this is sort of my first part of the talk. Obviously, it's already 6:40, so I only have about 15-ish minutes maybe to talk about the second half. But if there's questions on this half, I'm happy to stop and answer.
So we have a lot of students that are kind of at an introductory level online. And I thought that they would probably find it fun to learn what you mean by cumulative regret, because that's not a function you learn in Introstat. So can you just give a kind of high level, not high level, just a really rough idea of
Yeah, no, so
what this
the
is?
easiest way to think of this, no, that's a great point. So in a simulation, so we're gonna think in a simulated environment. So you have at time 40, I tell you the current context of the individual. There's 2 things that are happening. One is you have your algorithm. It has to make a decision on what action to take, right? So you decide to send a message. There is a true reward associated with sending a message. Now imagine God coming in and it knows the true model of everything. So it knows the best action to take at that time. Regret is your comparison of what God would have done to what you did. You can never do better than God, so you always have regret. But you can sometimes do as well as him. So at every single time, you're basically saying, did I do much worse than I could have possibly done the best version of? So at every time you have a best action and your action, sometimes you get it right, sometimes you get it wrong. So you have a little bit of regret every time. And cumulative regret is just the sum of those terms. So you're just summing them up over time. And you're saying, okay, how often am I getting it wrong? You want these curves to basically, you can never usually do better than root t, meaning it usually looks like a square root curve, which is why you have this sort of trajectory. Early on, it's kind of linear, and then it kind of tails out. Higher regret is worse. So basically, higher regret means that you've made more mistakes more often than another. One other thing I'll say about them, and for those of you who want to read more, because that was a very high level point. There are like 3 different true definitions of regret. One's like a Bayesian regret. They're all just different versions of this notion of you had to make a choice. There was a right choice. So you pay this regret. The different definitions are just, are you taking expectations over context, or are you just actually, for this particular sequence, defining the regret?
Thank you. I hope that people can find a way to use this term in their daily life.
Yes, we all have cumulative regret, and hopefully it's routine. Other questions online?
I'm not seeing any.
Okay, cool. So The other part I wanted to be relatively brief, so I'm glad to have a little bit of time to talk about it. So this is this notion that, let me pause here for a second. So I have a lot of slides on inference after optimization. I wanted to give you just a high level discussion. Here, right, I've run an RL agent. The RL agent has a notion of what variables matter. But at the end of the study, you can go back and decide, okay, these ones are actually the ones I should have focused on. So for example, you may not have included ones you thought were important, or ones that you included are actually not important. You want to learn that with the data you've collected. So how do we do that? We use causal inference techniques. And so to set up the estimand that I want to talk about, I'll just spend a few slides defining it. So as I mentioned before, you have a sequence of observations, actions, and rewards. So here you have O, A, Y to denote that sequence. OT is your observations, AT is your randomized treatment, and YT plus 1 is your outcome of interest. In heart steps, this is the observations are just the wearable data. AT is binary, did you send a message or not? And YT plus 1 is number of steps in 30 minutes. The types of effects we're going to define, now there's many ways you can do this. I'm just going to talk about the most common one. So what we often are interested in MRTs is this notion of a moderated treatment effect. And this is the idea that given where you are right now and what context you're in, so that's this ST variable, so conditional on your current context ST, or your current set of values of the potential moderator ST, I want to look at the causal effect of sending you a message at the current time compared to not sending you the message. So this effect, we call it a causal excursion effect. Why do we call it a causal excursion effect? Well, it's causal because you're looking at a contrast of two potential outcomes at a given time t, so you're either sending the message versus not. It's conditional because you're conditioning on potential moderators, ST. It's marginal because you're marginalizing over all other potential moderators. And it's an excursion because if you look carefully here, I'm looking at AT equal 1 and comparing it to AT equal 0, but there's a bunch of treatments you could have gotten in the past, and you got them under a policy that I've run. And so you're taking a little excursion from the policy that I've implemented. So we call this the causal excursion effect. It sounds fancy, but in reality, at every time t, you're standing there and you're saying, I've arrived here in this potential set, with this variable st, I'm in this state st, and I want to look at the little effect at the next time of sending a message versus not. That's what we're defining here. And there's a tool from the 2018 Barufka et al. Paper called the weighted sum of these squares, and this is a method to estimate that effect. So what you assume is a causal effect, a causal model, ft of st transpose beta, and you basically say, I'm going to fit a weighted regression model. So for those of you who've seen regression before, right, I think pretty much everyone, this is a least squares problem you're solving. It's a weighted least squares, so you have a weight sitting out front. So what is the weight doing? Well, the weight is accounting for the fact that the randomization probabilities are potentially different depending on the different histories. Why is this not just a regression model? Why isn't this just a model for y given h and a? It's because of the centering trick. So here, we're not interested in building a model of y given the history and action. We're interested in just the treatment effect. And so the centering just allows us to read off a treatment effect, a causal effect, without assuming this is a full correctly specified model. It's sort of a standard causal inference trick to allow you to look at treatment effects without assuming you got the whole model correct. I'm going to skip a few slides that I like talking about, but I don't have time. So power randomization slide I want to skip. So how do we actually do this in a more modern way? So I just want to explain the most recent up-to-date, this is like 2025 version of WCLS. Well, now what we end up doing is actually, instead of fitting linear models, we use machine learning algorithms. So I don't know how many online have heard of using double machine learning. I don't know if that's a common term for the students online. It sounds very fancy, but I just want to show this to you to explain. When you hear ML people say double machine learning, it's really simple. All they're doing is they're saying, I have two parts of my model that I'm going to fit. I have a part I don't care about, these control variables, and I have a part I care about. So what am I going to do? Well, the part I don't care about, I'm a machine learner, and I don't want my model to be linear for y given the history. I don't think that's a good model for the outcome given the history. I'm going to fit a machine learning model. And so the problem with doing that is you can't do everything at once. There's some issues around regularity, sort of statistical issues that come up. And so what they do is they split their data. They use part of the data, sort of the sample one, the training component, to fit a machine learning model to predict the outcome. And then they just plug that into my weighted standard least squares. So they basically say, I get to use machine learning to predict my outcome. And then you can do everything we just talked about in terms of the weighted standard least squares. This is a nice technique. What it allows, the reason domain scientists like it is because they don't have to think hard about what control variables to include, what model to write down. They can just do the machine learning model and forget about it. My negative comment on it, even though it's almost time to
So
go.
what comes out of the machine learning that goes into the regression?
Sure. So basically what it is it's just a prediction of y given the history. So basically you're just saying, okay, there's a bunch of history I could throw into this into a model. It's every observation I've collected up to now. You might make a really simple version of that history, so some feature vector. And then instead of saying I know how to make it a linear model as a function, there's a linear model from this feature set to my y, just let a machine learning model figure it out. What that allows them to do is basically just tell you what features might matter. And then you just don't have to think about building that model together. They can just run the machine learning algorithm and let it go. Yeah. So this is the one part. The other part, and this is what I'm very interested in, and I think is underappreciated in mobile health, is this issue that I mentioned with the statistical calibration. So a lot of the studies we've run, we think of them as randomized, but in reality, we don't know the true randomization probability because software engineers, not to blame all of them for everything, but they get things wrong sometimes. And so we actually have to think more about it as potentially an observational study, where sometimes we know the randomization probability, but we might get them wrong. The second component is we often have missing data, and these WCLS algorithms don't handle missing data well. They basically assume complete case analysis. And so we extended these methods to just allow for those components here. And so we have this nice algorithm that Hera Shi, who is another student here, came up with, and all it involves basically a sequence of little machine learning algorithms and then a very simple least squares problem. So for the applied person, we basically don't show them step 1 through step 3, and we just say you're fitting a really simple least squares. So this is the final step. What is going on under the hood is we're basically using that machine learning machinery that I mentioned before to basically just fit a few different models. So we're fitting the model I mentioned before, that's this G, and then we're just fitting a model for the probability of missing data given the history. Okay. Wow. Thank you. So I'm gonna show this and then I'm gonna stop talking. I was gonna talk about selective stuff, but I think I'd rather see if there's questions. So why did we build all these tools? Well, there's a study called the Intern Health Study. It's one of the ones I mentioned that we're doing RL for moving forward, but it's existed since 2018. Every single year, medical interns get an email saying, hey, would you like to be part of this study? And they say yes or no. And so you get roughly 1,000 interns across the US who say yes. What they're given wearable devices to follow them over the course of that year. And they know that's a year of heightened depression, heightened anxiety, heightened mental health issues. Why? Because they're in residency, and that's a really rough time. My sister's in residency, and yeah, it sounds miserable. She also had a kid during residency, which I was like, how is that even?
How is that possible?
Yeah, so it seems very difficult. So the idea behind this MRT was to focus on trying to improve mood, physical activity, and sleep in interns. The study was pretty straightforward. It was every single week you were randomized to a particular type of week. So you were either focused on mood, activity, or sleep. And then every single day you were just randomized coin flip 50-50 between sending a message or not. Those messages were like life insight type messages about your historical data. I'm going to focus not on efficiency, but I'm going to tell you the story, which is if you look at the data, this is a very simple design. You think, what could go possibly wrong? What ends up happening is if you look at the rough marginal distribution of treatments, it does look 50-50. What ended up happening, and you don't notice this if you're not careful, is if you look at the 2x2 of week on, week off, 2x2 of each week paired with the next week, it turned out that every week you received a message, you were automatically not receiving a message the following week. And so there was no randomization sometimes in the system. Why? Because software engineers are not statisticians. And so they were like, they just deterministically decided, we're going to restart you every single time you receive a week on. So it's a different study. And so the DRWCLS, we designed it to pick up on that. So instead of just trusting that the design that they implemented was the design we had hoped for in running WCLS, we actually, DRWCLS can pick up on this. Secondly, there's a lot of missing data, there's a lot of missing outcomes. The way they handled this was they actually built an entire imputation strategy. But if you've ever tried to impute temporal data, time series data with long time series, it's a pain. And so this method also allows you to use machine learning to avoid that. And so what you're seeing here is a time varying effect. So in light blue is the WCLS effect. Early on in the study, it seems to be a positive effect on step count of sending messages, and it dissipates. This is sort of the standard story. And then this is the light blue, is that early on mood messages have no effect, but later on have a negative effect on mood, which is not good. Negative effect on mood means you're making people more upset. So, what ended up actually happening, if you account for all the complexities, the problems with DRWCLS, is that positive effect seems to wash away, because in reality, those times that were zeros were not actually randomized to zero, those were deterministically zero. They sort of inflated the effect early on. And then the effect is actually in a different direction on this one. So you see that the mood effect early on is very negative, and then it dissipates. Why? Okay, this is my sister's interpretation. As much as I've asked a few interns. It's because early on, you're getting messages to try and improve your mood, but you're already in residency, and there's just qualitatively, you're getting annoyed that you're being told to try and improve your mood, but you're in your 6th week of this really intense program. Later on, you're already burnt out. And so there really is no effect of the messages, because when you're burnt out, you're burnt out. And so this story makes a lot more sense, and it also reflects the fact that what they were hoping is maybe there's a positive effect that dissipates and becomes potentially negative, but it turns out by using DRWCLS, this effect is different, and you should just get rid of mood messaging pretty much throughout. And so this is the benefit of this kind of method. Okay, I'm not going to talk too much about this. I'll just give you the very high level statement, and then I'll stop because I have about 1 minute. So we've taken this to the next level. So we've done a lot of fancy things. And I just want to point out the last thing that we've done. This is the most recent. I got too excited. I threw it in the slides, but I didn't think I had a lot of time. So the issue is the following. How did I choose my ST in my set that I talked to you about previously, right? So what we typically do is we ask behavioral scientists in the clinical trial to write down the primary aim, which is just like a single variable that they think might moderate treatment. And in the secondary, there might be 1 or 2 other ones. What they then do in an MRT is they get to their exploratory phase, which what that means is they go through all 50 other variables they've collected and one by one use WCLS to see which ones are significant. Now they have a list of 25 and they get very excited about them. And I don't like that. And so what I decided to do is say, okay, maybe there's a more holistic framework we can have around exploration, a framework around exploration analysis that's more principled. So the issue again, high false discovery rates with these sort of sequence of single moderator values. So what could you do? Well, you could tell them you need to write down all 50 variables you might include, and we're going to fit a joint model for all of them at once. So instead of going one by one, you're going to fit a big joint model of all of them. What's the problem? You now have a ton of variables you might select, so you want to do some selections. So you're like, oh, I want to do a penalized version, so like a lasso or something like that. The problem is I can't just hand them a point estimate like the lasso, where I just say, hey, this is what the lasso spit out. Here are the 3 variables it's selected. Have fun. I want to actually say something in terms of giving them uncertainty quantification about the variables it selects. And so what we designed, and I'm not going to talk too much about it, is there are methods from what's called the selective inference literature that allows you to do this. They have flaws. Those flaws basically are that they give often infinite width intervals. So I can't go to my collaborator and say, hey, I selected these 3 variables. The interval is from negative infinity to positive infinity. Thank you so much for your time. And so instead, what we came up with is a randomized version of the lasso. So what you do is you basically inject noise into the system. I won't go into the details here, but I just want to show you what ends up happening and why I care about the method. So the reason I care about the method is in many of these studies, so Valentine is basically a version of heart steps. By doing one by one analysis, people really thought that time and study mattered a lot in these physical activity studies. And it kind of intuitively makes sense, right? Early on, you might be excited to be in the study, you're really motivated, so you see an effect, and later on, like 2 months in, you're sort of less motivated. And they thought there was no way to capture that. And by using this analysis, actually what we found out is all of those variables drop out if you don't do large single variable analysis. Instead, what you pick up on is baseline step count matters a lot. How active are you when you enter the study? And that's offset by how active are you right now, so in the previous 30 minutes, and how active are you in the prior week. So it's sort of the picture in time was sort of hiding the fact that what really matters in these physical activity studies is your baseline activity, and it's modulated by how active you are over the course of the study. And that picture comes out a little bit nicer when you do these sort of selective inference techniques. Okay, cool things. Yes, conclusions, fun things. I'm gonna pause here and just say thank you. And I hope you learned a few things. My main takeaways I want you to have are just, there's some interesting things in mobile health for those students who are interested. My goal was an overview, so not to say like dive too much into one, but to say if you're really interested in decision making, there's really interesting problems there. If you're interested in causal inference, there's interesting problems here. But overall, to do good work in this area, which I like it, is because you have to work with a mixture of domain experts, engineers, statisticians, and CS people. And so it's quite nice from my standpoint of balancing statistical novelty with actual real world impact. And I'll stop there. And thank you all.
Wait, I have a question from one of our online chat people, Walter. Another Walter. Another Walter. I have a naive question, which you might have mentioned at the beginning. It seems like you cannot use some simple technique because you have a lot of noise and a huge data set. What's the size of the data set?
This is the first part of the second part. They say at the top.
They didn't say.
He says.
Yeah. So in
But
these
it-
studies, I can give you a rough sense. So the small MRTs, the small RL studies are like 100 people, so they're very tiny. So you have to be very careful about you're not going to have thousands and thousands of observations to just, it's not like the LLM large data kind of settings where it doesn't really matter. You have enough compute, you just run some massive model and it'll all work out. Here you have to be a little bit more thoughtful. The largest study we've run is the intern health study, which has 1,000 people. And there some interesting scaling issues come up, but the biggest problem is you do have the signal to noise problem. Even with 1,000 people, the heterogeneity in signal to noise the signal to noise is so low and the heterogeneity is so high that you have to be very thoughtful about how you pull information and carefully do that. Thank you, Walter, for that question. Other questions?
Suraj, you can ask him anything. You should ask him like when you can set your defense date, something.
I'll do that after the recording.
No. Other questions?
I mean, I just think that the context of I don't know the right term to use, but when you mentioned the burnout, because in medical students, an interventional study in situations like that has to have some thought ahead of time because of those very, very things.
Yeah.
And so, I mean, it's just like, if you're gonna try to send messages to somebody that's just entered the opium den, it might behavior be different after a while,
So yeah, I'm totally with you. I think my key takeaway, and this is where like RL won't save everything, right? So like people think that these techniques can just immediately save a badly designed study because they're like, oh, we'll just figure out who it worked for and who it didn't, and it doesn't really matter how I designed these initial phases. And whenever I hear that kind of thinking, it definitely, to your point, it's like, no, you have to actually put a lot of thought into it, because in reality, so all these algorithms require you to start in a pretty good spot, and they're really just optimizing beyond that a little bit. So if you start in a bad spot, they're just not going to learn much, and they're just going to say, okay, this is a bad idea, turn all of them off, right? So that, and so that's my main point to my collaborators, is I do think a lot of them see AI or RL as these sort of, it'll save my badly designed intervention. Yeah.
Just practically, how do you deal with like do not disturb settings on phones and all these interns? I imagine they're going into some surgery and The last thing they want is this ping, ping, ping.
So interns, you have to be very careful with how many times you ping them, when you ping them. So we often do is we'll set a time for them and say, when do you think you'll be available today? And that way it's sort of matched up when they think they're like able to receive it. And it's usually only once or twice a day maximum. Like you are not pinging them like crazy. They do have do not disturb capabilities. A lot of them don't turn it on mostly because they just start ignoring it and they just, it's almost, you can tell that they aren't looking at the app or anything like that. So what you often will do with them, the thing that annoys them the most, is telling them things they already know. You're not getting enough sleep. Yeah. Right, like of course I'm not getting enough sleep. So so you have to be very careful with what kind of insights you're giving, right? So people will say life insights, and often life insights is just shorthand for we're giving you data back to you. But if that data, you just know it already, right? It's not an actual life insight. It's just, thank you for telling me I was sedentary on the day that I was like in meetings from morning to night. That's not very helpful. And so there's been a big push to make all those kinds of things more useful to the participant. So either things like you find out what they're actually motivates them, you use that to provide the interventions and tailor them more to that person. A lot of the time, the life insights have to be tied to like actual outcomes they care about. So a lot like step count is often one that they actually might care about. A lot of medical interns are okay with that being something because they want to be somewhat active, and not just sedentary. And so if you can say, okay, look, if you get a little bit more sleep, this is the positive outcomes that you could potentially see, and this is how I can get you there. It's a little bit more meaningful to them. But yes, disengagement, turning off the phone, these are like the big two ones with mobile. The other way we've gotten around it, and this is an interns would be not possible, but in chronic illness populations, when that happens, you typically have so you're thinking of the mobile intervention as the first stage option, and when it's failing, you have second stage options you can turn on that are more expensive. So like substance use populations, you're thinking of the mobile option as like, if you can get someone to use this and it helps them and they don't need to go into the clinic once a week, great. But for 30% of the population, that's not going to work. And so for that 30%, you're going to trigger sort of second stage, more intensive options. Raj said he didn't have a question there.
Can you talk a little bit about the difference in statistical significance versus real world impact when you're evaluating a method? For instance, like a step count of 50 might be, an increase of 50 might be statistically significant, but is that clinically relevant?
So you'll see most of these papers will be like, we found a statistically significant effect of this intervention on step count, and you'll look at it and you'll see like the effect was 200 steps or something. So yeah, I mean I think what you end up having to do is you end up having to translate that into potential impact on outcomes you care about. So like a lot of the time, if you can't show movement in the distal that you actually care about, so in like cardiac rehabilitation, increasing step count is really important, but really what matters to the like Jesse Golbus is the clinician I work with, is like the 6-minute walk distance is their be all end all measure at 6 months. And so there you kind of have a guide, like a guiding post of what you're going to aim for. The first study, you might not target that. You might just say, okay, I have something significant, but usually what you need to show is that within 2 or 3 studies, you're moving that target of that clinical outcome, that meaningful outcome. And so like in mental health, where I do a lot of my other work, it's, do you see changes in the PHQ-9, or do you see changes in suicide ideation, if it's a suicide prevention study, and not just, did you get them to use the app, which is like often the other outcome we focus on.
All right, thanks very much for coming again, and maybe in a few years we'll have you back. It was a great talk. Loved it.
Thank you. Yeah, if you have follow-up questions down the road, please feel free to ping me. I have email, so love to hear from you guys.
Okay. I'm going to officially stop the recording.